we've been talking about geometric series. We said we could find the formula for S sub n, which stands for the nth partial sum. Which you can think of as really the sum of the first n terms. All right? So the first term in our series is a plus, to get the next term in our series, we multiply the first term by r, the number that we're going to multiply by every time. Now, I don't know if I defined this before, but this number r, that is usually called the common ratio. Okay? Common ratio because if you take any two terms and divide them, that's what you're going to get, right? So let me show you what I mean by that. This is ar squared plus ar cubed plus all the way up to get to the nth term, you'd have ar to the n minus 1. Let me just explain what I was saying a moment ago. If you took these two terms to divide them, you'd have ar cubed over ar squared. You'd get just r as an answer. R is the ratio of those two terms. If you decided to pick these two terms instead, you get ar squared over ar, and you get r. Again, it's the common ratio. It's the number you get when you take any two consecutive terms and you divide the one on the right by the one on the left. There's an order to this when we write it down. Okay? We came up with a formula for this. We derived that the sum S sub n equaled the first term times 1 minus r to the n power over 1 minus r. Let's look at a problem that utilizes this formula we have. So suppose you had, here you go, this sequence, 1 plus 2 plus 4 plus 8 plus up to, and let's pretend we said n is going to be 9 terms. So what I'm asking you to do is find the sum of the first 9 terms of that series. Okay? So what you need to do is identify two things for the formula. The formula, S sub n, requires, let's make a note of this, it requires the first term, which is a, requires the common ratio, and it actually requires 3 things, the number of terms you want to add, n. So according to this, S9, see n is 9 in this case, would equal the first term, which is 1, times 1 minus the common ratio. So you always have to look at the series to figure that out. Well, I must have been multiplying by 2 every time. So 2 is the common ratio to the 9th power over 1 minus 2. So if we take the time to evaluate that, we'll get an answer. So what do we have here? We have 1 minus 2 to the 9th. There we go. So this is going to be 1 minus 512 over negative 1. Well, that's negative 511 over negative 1, or 511. Okay. Sometimes when you're asked to do these problems, you won't directly know what the number n is. Sometimes you have to do a little bit of thinking first to figure it out. So, for example, suppose you were asked to sum these problems, this sequence. So, negative 2 plus negative 12 plus negative 72 plus negative 432 plus negative 2592. So you look at this first, and then maybe you would spot, hey, this is a geometric series. How do you know? Well, you should look and see if you can multiply by the same number every time to get the next term. So if we multiply negative 2 by 6, we get negative 12. Well, let's hope that happens again. And sure enough, it does. This also would be 6, and so would that, and so would that. So this is a geometric series. Okay? Without working too hard here, you could actually count them up. You could say, hey, wait a minute, there's 1, 2, 3, 4, 5 terms. So that means that n is 5 in this case. By the way, we won't always have the luxury of counting. We'll deal with that in a minute. Okay? So if I want S5, it's just going to be negative 2 times 1 minus 6 to the 5th over 1 minus 6. And then whatever that turns out to be, you can figure that out. Okay. Let's look at an example where it's less obvious what n was. In this case, we could just count how many terms we were interested in adding. So let's look at this one. Ready? Suppose we had 3 plus 4.5 plus, you should pause for a minute and try to figure out, hey, what would have come next? If we think about that, to go from 3 to 4.5, we must have multiplied by 1.5. You can get that by dividing the numbers if you like. Okay? So that's going to be a common ratio. We're going to multiply by 1.5 every time. So the next thing on the list is 6.75 plus, and let's pretend now we went for a long time, and then we had plus this. Suppose we had this number, 9975.77019024. Question is, how many terms were on the list if that's the last number I get? So in order to figure this out, let me just ask you another question. Let's just for a minute think what came next after the 6.75 that is, times 1.5 gives us 10.125. So the next number on this list was 10.125. So here's what I'd like you to observe. To go from the first term to the second term, so this is the first term, this is the second term, I multiply by 1.5 once. Right? So to land on the second term, you only need to multiply by the common ratio one time. To land on the third term, you started at 3, you multiply the common ratio once, you landed on 4.5. You're going to have to multiply by the common ratio again. So to get to this third term, we multiply by 1.5 twice. Okay? And then not lastly, but to get to the fourth term, you multiply by 1.5 3 times. So what does that mean? Well, that means that if you wanted to get to the nth term, so maybe we would write that a sub n. This is notation meaning a is the number in the nth position. We would take our first number a, which in this case is 3, but our first number a, and we multiply by the common ratio. And if we want to land in the nth position, we really don't need to multiply by r n times. We can multiply by r n minus 1 times. Now, how do we know that? Well, think about what we just said up here. To get to the second term, we multiply by 1.5 only once. To get to the third term, we multiply by 1.5 only twice. To get to the fourth term, we only multiply by 1.5 only 3 times. So if we were going to get out to the nth term, which is some number on the list, we would have to only multiply by r n minus 1 times to get there. So there you go. You actually have it now. I need to find out what n is, but I can do that. I can say the nth term is 9975.77 ... has to equal the first term, 3, times the common ratio, which we know is 1.5, to the n minus 1 power. And this is an equation that we can solve using logs if we want. Right? So what we do to both sides first, we divide by 3 to get that 3 out of there. So I'm going to do that. We divide by 3. Bear with me for a second. Divided by 3. Then you get this. 3325.25673,008. This is an approximation from the calculator. So n might not be a perfect integer, but we'll know what it is. Equals 3. I'm sorry, not equals 3 anymore because 3 is divided out. Just equals 1.5 to the n minus 1. And we've talked about the fact that if we want to get an exponent and solve for it, we could take the log of both sides. So we'd end up taking the log of this expression, the log of 33.25 ... would equal n minus 1 times the log of 1.5. We could divide by the log of 1.5. So we'll have the log of 3325 point whatever, a bunch of decimals, over the log of 1.5 equals n minus 1. And then you can see the last thing we would simply do is just add 1 to both sides. I'll put plus 1 over here. That expression is our answer. This would just become n, which is what we want, and we would know how many terms are on our list. Let's figure out what that is. Stuff in, you get n equals 21. So that means there were 21 terms on the list. And now you're ready. The formula for S21 is the first term, which we said was 3, times 1 minus 1.5, right, to the, let's think about it, to the 21 over 1 minus 1.5. So whatever that is, it'll be the sum of this series. So what we're going to start talking about now is what's called periodic investing. Periodic investing. I can't even spell it. Forgive me. Stop that. All right, so periodic investing. And let me show you an example of why this is different from things you've done in the past. Usually, when you first learn about exponential functions, you think of things like this. I'm going to invest maybe $1,000 at some APR, maybe 3% annual percentage rate for a certain amount of time, okay, for maybe 3 years. Okay, let's go with 4 years. So this is usually what you face, and you usually ask the question, what's this account going to be worth in 4 years? So what do? You say, I'm going to take $1,000 times 1 plus the interest rate of 0.03. You can see we're compounding annually right now, to the 4th power. Okay, and then you could type that in and get a result. About $1,170. A little less than that, but whatever. Okay, my claim is that's not how people really invest money. Okay, what people typically do is they make periodic deposits. So maybe every year, okay, we deposit an additional $1,000. That's more realistic. People don't usually just stop at the bank one time, drop off some money, and never go back. Normally what they do is they go and they repeatedly add money to this account. Okay? So let's start considering what the value of this account looks like over time, and then maybe we'll see why I was talking about geometric series and adding them up. Okay? So let's start with this. I'm going to say let E sub n equal the balance, okay, in the account at the beginning of year n. I guess we'll say that. All right? So, what can we say then? Or at the beginning, we could say the beginning of year end, whatever. That's what we'll do. All right, so we'll say it that way. And if that's the case, then what happens? Well, B sub 0 is the amount of money that you put in the bank, right, at the beginning of, well, we'll say this, B sub 1, actually. The beginning of the first year. At the beginning of the first year, you show up and you have to decide what you're going to put in. Maybe we put in $1,000. Okay? All right, so now what happens? Okay, that's the beginning of year 1. The beginning of year 2 shows up, and you've had this money, this $1,000, in the account for a whole year. So what the bank does, they say, thank you for leaving that money with us for the whole year. We're now going to give you 3% of that money that you left with us for the whole year. So they take this number of 1,000, they do 1,000 times 1.03, and that's what you get to keep. Okay? Because that's the $1,000 you originally deposited, multiplied by 1.03, which adds 3% to the value of your account. Okay? Now, what do? We said it's more realistic if at the beginning of year 2 you make another deposit. So here's what we're going to do next. We're going to say, all right, you're going to add another $1,000 to this because that's what you've decided to do. You've committed that every year you're going to show up at the bank and add an extra $1,000 to the account. So this is how much money you really have at the beginning of year 2. You have all the money that you earn interest on during year 1, right, plus the extra $1,000 you just deposited. Okay, so then another year goes by, B3. And if we think about it, the beginning of year 3, that original $1,000 you deposited would now get interest another time, right? So it got interest during the first year. It gets interest again because you've left it in the account for an additional year. So what about this? Well, don't forget, at the beginning of year 2, you stopped up at the bank and you gave them $1,000. That money's now been in the account for a year. So now that earns interest. That earns some interest from you during year 2. And then, like we said in this story, you've committed to depositing $1,000 every year. Okay, so I'm going to rewrite this first term because I can. I'm going to rewrite that as 1,000 times 1.03 squared plus 1,000 times 1.03. Actually, I just won't do that. You can just leave it in blue right there. Okay, let's do one more year, and then I think we'll see a pattern here, and we'll be done. All right, so let's pretend the beginning of the 4th year comes around. That original $1,000 has earned interest for you twice. It's actually going to earn interest again. So you're going to have 1,000 times 1.03 squared times 1.03, because this was the amount of money I had in the account for the year, and it got interest during the whole year. Okay, let's go to this $1,000, the blue $1,000. That's been in there another year. So this is going to be 1,000 times 1.03 times another 1.03, because it was in there for a year. That $1,000 deposit you dropped off, that's been in the account for a year, so that's going to multiply by 1.03. And then lastly, you decide to deposit another $1,000 in the account, because that's what you've committed to doing. All right, so let's write this in a slightly more compact form. So we can say that the money in your account at the beginning of the 4th year is equal to 1,000 times 1.03 to the 3rd power plus 1,000 times 1.03 to the 2nd power plus 1,000 times 1.03 plus 1,000. Okay. Maybe we're going to stop after 4 years. What I want you to do now is take a careful look at that expression and tell me what it looks like. So this is a geometric series. You know that. And your common ratio here, the number you're multiplying by every time, is 1.03. And the initial investment, the A0 is the first term I should say, is 1,000. There it is, over there. Okay? I mean, you could usually we see the first term that hasn't been multiplied by anything over here. You could certainly reorder them because not subtraction, but addition is commutative, right? So it looks just like what we want it to look like, which is a geometric series. And now what's really nice is I know how to find this sum, don't I? Right? The sum of this thing would be equal to the first term times 1 minus r, which in this case is 1.03, to the number of terms that I have. Well, I have 4 terms, and then I'm going to divide that by 1 minus r. And now I know the value of the account at the beginning of the 4th year, which is, the answer to this is about $4,183.67, something like that. So that's what this account is worth after at the beginning of the 4th year. So now, I can tell you for most people, when they start a career and they start working, they think about investing money for retirement so that when at some point, maybe if they can't work as hard enough, they have much time to work, or they're not physically able, they'll have some money saved. Imagine what would happen in an account like this after, say, the beginning of the 25th year or the beginning of the 35th year, which isn't uncommon, right, for someone to work between 25 and 30 years over the course of their life. Well, if we give it a little bit of thought, let's just go back and look. At the beginning of the fourth year, we had 1, 2, 3, 4 terms. So at the beginning of the 25th year, we'd have 25 terms. So we'd have 1,000 times 1 minus the common ratio to the 25th power, because it's 25 terms, over 1 minus 1.03. And then we can go write this one out real quick, too. This would be 1,000 times 1 minus 1.03 to the 35th power over 1 minus 1.03. So this is really going to show us the power of a periodic deposit. Okay, so watch this. I'll change that 4, basically, just changes to a 25. I hit enter, and now I have 459. Okay, go an extra 10 years. Okay, go to 35, and now you're looking at 60,462. Okay, now this is if you're just putting $1,000 away, and you're only earning 3% interest. Okay, so that's not to be doom and gloom. If you're going to go to the bank account, to a normal standard bank, if you got 3% interest over 35 years, that would be good. Banks don't pay a lot of interest. But if you were to carefully choose some bonds or some other places to invest, that interest rate of 3% might actually be something more like 7 or 8% over the long term. Okay? If you could do something like that, watch what happens. So let's pretend you're going to get 7% interest over the long term instead of 3% interest by carefully choosing investments. That $60,000 would instead be $138,000. So that would be pretty nice.